Hello, and welcome to Lecture 14, covering Section 5.6 on the topic of mechanical energy and its conservation. So this section and these lecture notes are going to be all about solving a particular type of problem. All right, so let's get some key terms done and established. They're not anything too big. They're just going to kind of reinforce some ideas we've already talked about. Okay, so I've already mentioned mechanical energy, but I want to redefine it in this lecture. It is the energy of gravity, springs, and motion. Okay? Or more in more technical terms, it is a category of energy that includes kinetic energy, gravitational potential energy, and elastic potential energy. All right? It excludes things like heat energy, electromagnetic energy, nuclear energy, and any other forms of energy. All right? That's it. That's mechanical energy. And it's what we're talking about in this section. Okay? All right, kinetic energy, we've definitely already talked about that. This is just copied over. Energy of motion. Energy is a quantity that either can do work or is created by work. Kinetic energy is one form of energy, okay? And it is a scalar unit with, it is a scalar quantity with units of joules, okay? And obviously so are gravitational potential energy and elastic potential energy. Okay, now what is an isolated system? This is new. Okay, an isolated system is a group of objects totally isolated from the outside world. And when we say isolated means no exchange of mass or energy with the outside world. That's the definition of isolated. Okay? And it turns out that a block sliding downhill without friction is an example of an isolated system. So kind of generally speaking, it's basically anything without friction is an isolated system. Okay? Now, what is the principle of the conservation of mechanical energy? So here I just call it a rule about energy. I know it's kind of general, maybe too general. But I do mention I like the idea because really a principle is just a rule. So is a law that's never been broken. Okay? And specifically, it states that an isolated system, or in an isolated system, mechanical energy is conserved, which means it can change form but will not disappear. Okay? So in an isolated system, without friction, mechanical energy is conserved. All right? It is very useful for solving positions and velocities between points of a system. Okay? I'll say this again, but you know what it's no good for at all? Tells us nothing about time. Nothing. You know, so I have the kinematic equations that can like solve for time. Well, these equations cannot. All right? Now, that's almost not relevant. We're not going to see it mentioned, but I don't want you to have false expectations. You're never going to see anything like how long does this take? And if I do ask you how long it takes, you're not going to use energy methods. Okay? And I'll mention that again because it's good to be aware. That said, it's not the main focus because the main focus is a new technique for solving problems. Because ultimately, this principle of conservation of mechanical energy, it's just useful, right? Energy isn't new physics. It's just a useful tool. Okay? All right, here are our key formulas. Okay, so here is just mechanical energy, right? So sometimes we kind of just define it, right, you know, in a particular problem. Subscript mech for mechanical. It's the sum of kinetic energy and potential energy. Here I'm using Ke, okay? Again, sometimes I'll use K, but here I'm using Ke. Okay, kinetic energy, potential energy. Now notice this subscripts in the next line, 1 and 2, okay? So essentially that's, and the same thing's going on down in the next line, which I'll elaborate on in just a minute. But that's the idea that we have conservation of mechanical energy between points 1 and 2, okay? So in terms of general terms, Ke1 would become 1/2 mv1 squared, because the only thing that's changed is the velocity. M is constant, 1/2 is just coefficient. The potential energy has two terms, right? It can be a combination of gravity and elastic or just one or the other, all right? And so then potential energy 1 would be this whole sum here, okay? Those terms are equivalent to each other. Okay, so in other words, PE1 would expand out to mgy1 plus 1/2 k sub 1 squared, okay? And you know why? So basically, it's the only thing that's changing is the position, the vertical position, and the spring compression. All right, K doesn't change, G doesn't change, and M doesn't change. So those don't have a subscript on them. Okay. Now, why 1? Right? Because we're kind of used to maybe using initial and final, or not and instantaneous. You know, the subscript 0 and then instantaneous without a subscript at all. Well, the reason that we're using a kind of a whole new subscript here between 1 and 2, like 1, some point, and then some point 2, instead of initial and final, is because really kind of often there might be a third point. And it's also, in terms of energy, you really can't just jump between points. So it's not even so much about initial and final. It's just the idea Because it doesn't matter which one's initial or final. It's just the idea that when you compare between the two, they have to sum up to the same value. And so the conservation really makes sense by just calling it point 1 and point 2. A and B would also make sense, right? But it's really because there's no order to the points. There's just the idea that the value of the sum of kinetic and potential cannot change, okay? All we're saying is that E mechanical is a constant for an isolated system, okay? That's what we're saying, okay? But let's put it to practice. All right, so 3 types of problems, all right? Type 1, problems that involve one type of potential energy and conversion to kinetic energy. So those are the simpler ones. Type 2, fairly complex problems that involve both gravitational and elastic potential energy. Okay, so both of them are going to be involved, like a spring and gravity, and a conversion to kinetic energy. And then type 3, fairly complex problems that involve gravitational and or elastic potential energy and require kinematics to solve. Okay, so there's something, either a question about time or there's something that you cannot solve without kinematics. Maybe a question about acceleration, because these energy equations don't tell you anything about acceleration. They don't tell you anything about time. Okay? All right. So let's take a look at example 1, which is a type 1. It's a problem that involves one type of potential energy and kinetic energy. A robotic rover with a mass of 941 kilograms falls off the edge of a huge cliff on the surface of Mercury. Mercury is known for its huge cliffs. Really. The rover is in free fall for 28.5 seconds before hitting the ground. How much kinetic energy does the rover have when it hits the ground? If we take gravitational acceleration on the surface of Mercury, it would be 3.7 meters per second squared, which is approximately the gravitational acceleration on the surface of Mercury. All right, well, we use time and acceleration to find the cliff height. All right, so we find the cliff height to be 1,500 meters. Okay, and again, because we were given some time value. Okay, and I guess in that case, you could kind of say it's a type 3 problem, but it's so basic, I decided not to include it. Okay, it's more when there's a follow-up question. I guess I'm cheating my own rules. But anyway, then we're going to use conservation of energy between 2 points, points 1 and 2, except here I'm specifically calling point 1 top of a cliff, and I'm calling point 2 the bottom, just different subscripts, okay? And so then we have our energy at the top of the cliff is just gravitational potential energy because there's no kinetic, it's at rest, it starts from rest. And then when it hits the bottom of the cliff, it's got no more gravitational potential energy because it's reached the bottom. Think about the lecture on potential energy. We define our y equals 0 at wherever we want it to be, and here it makes sense to define it at the bottom of the cliff. Okay? But when it hits the bottom of the cliff, it is in motion, so then it definitely has kinetic energy. All right? We could also rewrite this as just PE top and KE bottom, especially because we're not trying to solve for V, we're actually trying to solve for KE. And so then KE must be just equal to mgy. All right? We know Y to be 1,500 from our kinematic expression. And so then we just plug in the mass, the gravity on Mercury, and we get that the rover has 5.23 million joules of kinetic energy when it smashes into the ground. All right, dependent on its mass, the gravity that where it is, and how far it fell. Okay, all right. So moving on to example 2. If a mining explosion gives a huge boulder with a mass of 2.22 million kilograms and initial kinetic energy of 13.3 million joules, then what maximum height will the boulder reach if its initial velocity is angled 77 degrees to the horizontal? Okay, so how's that angle going to show up, right? Well, okay, glad you asked. So here's the picture, all right? So the idea is there's some initial explosion that's going to release energy. That energy is going to immediately manifest itself into kinetic energy of the boulder. Then that kinetic energy of the boulder is going to transform into gravitational potential energy, okay? But only some of it, because only this component of the velocity will create kinetic energy that will actually be transformed into gravitational potential energy. This component of the initial velocity, the horizontal component, will just remain kinetic energy. It won't become gravitational potential energy because there's no force to create work to do that. So this one will just remain unchanged. The kinetic energy that is associated with the horizontal velocity will remain unchanged, okay? And that's what's interesting when you have components of velocity, is you have to realize that what that means in the context of energy, okay? But we're going to set this up like we will basically almost all of these energy problems. We're going to have a point 1 and a point 2. I'm going to take point 1 as immediately after the explosion and point 2 as when the boulder reaches its maximum height, okay? So then, there we go, E1 equals E2, right? This is basically the way we start these problems, which is, they're so formulaic. You just kind of write that down and then you collect your thoughts. Okay, all right, let's expand out E1 and E2. E1 will expand it out into KE1 and PE1, and then E2 will expand out into KE2 and PE2. All right, totally fair there, right? Well, PE1 is 0 because when it starts at the moment of the explosion, it hasn't actually gone up in the air yet, so it doesn't start with any potential energy, okay? Now, what about 2? What actually still has kinetic energy? Because when it reaches its highest height, it is still moving to the side. That horizontal component of velocity is unchanged, okay? All right, so now let's expand this out. All right, so what I've done is I've just rewritten KE1 in terms of 1/2 mv naught x squared plus 1/2 mv naught y squared, okay? And then on the left-hand side of the equation, my KE2 is 1/2 mv naught x squared, and then my PE2 is mgh max, the thing I'm trying to solve for, all right? Now, there's two terms that are like on either side, right? So this term and this term, so I'm showing that they cancel out. But we might want to show where they come from first, so let's do that. All right, so the reason that we have a term on the right-hand side of the equation at point 2 that has an initial subscript in it is because the component of horizontal velocity is unchanging. Think kinematics, think projectile motion, because that's what this is, right? It's projectile motion, but we're exploring it with energy instead of with the equations of projectile motion, okay? Furthermore, the reason that we know that the kinetic energy can be split into these two terms is a simple fact that the hypotenuse of our initial velocity vector is v naught squared is going to be equal to v naught x squared plus v naught y squared by the Pythagorean theorem. Okay, we're so used to seeing the Pythagorean theorem when we take the square root of both sides, and then it's got a square root in it, but it doesn't have to. And then in that case, it's nice because then we can then just distribute the 1/2 m and turn one term into two terms. Okay, so make sure that math makes sense. Okay, so now let's simplify things. So then our E1 equals E2 simplifies with this right here. 1/2 m v naught y squared equals mgh max. The m's cancel because they're on both sides of the equation, so that h max is going to be independent of the mass. That's what we should expect because kinematics tells us it should be independent of the mass. All right, and then we just solve for h max. The square root of 2 v naught y squared over g. We don't know v naught y, okay? Because up to this point, we could have literally done all of this with the kinematic equations, but we were given an energy after all. We were given the initial energy of the explosion. Maybe we can use that to find v naught y, right? Well, we certainly can. Okay, so we'll acknowledge that v naught is just the square root of 2 times the initial kinetic energy divided by m. And this is the initial kinetic energy. All right, how do I know that? Just from the definition of kinetic energy. Is just 1/2 m v naught squared. Okay, that's the v naught squared that splits into components here. Okay, so then if we want just the y component, we would just take this expression and multiply it by sine of 77 degrees. That is our v naught y, the magnitude of v naught y that we will square in the expression for h max. All right, ends up being 3.37 meters per second. Substitute it in, put all our other values in, mainly just a 2 and gravity, because this one is on Earth, and we get a maximum height of 1.52. Not very high for such a huge amount of energy, but remember, this is a very massive boulder. All right? Okay, cool, right? So a lot of kind of like, starting with a basic idea and then making sure that we can kind of fill in the missing information as we go. Okay? All right, let's do another one. A tired and frustrated physics student rolls a ball down a ramp as shown. I wonder who that physics student is. The ball starts at a height of 9.5 centimeters above the table, all right? And the table has a height of 98 centimeters above the ground. What is the range of the projectile? This would make a good lab, wouldn't it? All right, so this is the height. We'll express that as the variable h. We'll call point 1 the release point, right, where it's starting on the ramp. It's going to start from rest. And point 2 we're going to call the moment that the ball becomes airborne, all right? Now you might wonder, why not put point 2 at the ground? Well, because since we're asking for range, it turns out we can't find range with energy. We can't. Because the only way we can find range is find time of flight, which means, well, we've got to use kinematics and acceleration because energy doesn't tell us anything about time. So range, definitely something you can't do with energy. That's why this is a type 3 problem, the purple one, okay? All right, so using mechanical energy conservation on the ramp, okay, so E1 equals E2. All right, so initially it's all gravitational potential. By the time you get to the bottom of the ramp, it's all kinetic, okay? Because basically I'm calling this point y equals h, and then right here I'm calling this y equals 0 for the purpose of energy. So then the velocity at the bottom of the ramp is just the square root of 2gh, okay? Which is exactly what you would get for free falling a height of 2gh because there's no friction on the ramp. And it turns out that gravity doesn't care if you're going on a angled ramp or if you're going straight down. You're still going to get the same final velocity. Okay? All right, but we saw, we kind of saw that idea with potential energy, didn't we? Okay? And then we're going to use kinematics to find the time of flight and thus the range along the floor. All right, so this is going to be our time of flight based on the height of the table. All right, solve for that expression. Get something, kind of another square root. In this case, the square root of 2h, uppercase h, over g. All right, and then based on the constant velocity of the motion in the x direction once our ball is airborne, we know then that the range, r, is just v times t. Okay, and it's the reason we can just use v instead of a component of v is because our velocity when the ball becomes airborne is entirely horizontal. Okay, well let's plug in v that we got from our energy. Okay, and by the way, we really did need energy for this, right? Because we couldn't have done this with Newton's laws because it's a curved ramp. And there's no way you could get, find the acceleration of the curved ramp because you would need, to do a free body diagram, but then your normal force would be a function of the curvature. You can't do it, okay? So you actually have to use energy anytime you have a curved ramp. Now, if it was like an angled ramp, that's fine, but the angle ramp wouldn't work, right? Because the angle ramp would give you a velocity that isn't entirely horizontal, right? So that's kind of an interesting thing here, really. This is new. We couldn't have done this with Newton's laws and acceleration. We have to use energy for curved ramps. Right? I want you to kind of appreciate that, okay? But anyway, look what happens when you multiply the velocity times the time, right? Substituting in the two expressions we have from energy and kinematics respectively, look, the g's cancel, and then, then we have a root 2 times a root 2, which just becomes a 2. We just get 2 times the square root of h times h. That's amazing, right? So the range is actually entirely proportional to the square root of the height above the table and the height of the table itself. Just the product of the two, in fact. It's independent of gravity. It's independent of the mass of the ball. Remarkable, isn't it? All right, plug in our numbers. And in this case, we get a range of 61 centimeters. All right, pretty cool. But definitely proportional to the square root of h, the height above the table. All right, cool. All right, moving right along, a pendulum. All right, now why is a pendulum a great type of problem for an energy chapter like this? For the same reason the curved ramp is. The pendulum takes a curved path. Okay, it's a circular path, in fact, right? Whereas the other one could be a parabola curve or something. This one is specifically a circle. Okay, that means that we can't use forces, right? Because, again, the tension, right? The angle between the tension and the gravity is going to change at whatever point the pendulum is at. So there's no way to find the acceleration. The acceleration is not constant, okay? It is definitely not constant. Now, it turns out that since it is a circle, we can actually find the acceleration. And the acceleration itself ends up being sinusoidal, okay? And we'll kind of mention where it comes from in passing. It's an idea that we'll see in a later chapter. But for now, the acceleration is totally unknowable. It is not solvable by Newton's laws as far as we can tell. By the way, the math you need is that you have to solve a differential equation, and the solution ends up being a sine equation, okay? But that aside, right? That's not relevant to this class or this problem. But the idea, what is kind of relevant and it's interesting as part of the concept is we need energy to solve this problem. Let's use it then, because the good thing is energy is a pretty simple way to solve problems. Okay, I hope it seems that way. All right, so we choose 2 points, points 1 and point 2. Okay, and we're just going to conserve energy between the two. Now, one thing we need to find is we need to find h, because I gave you L, which I label here, and I gave you theta, right? So, 38 degrees, but I didn't give you h, so you got to use geometry to find it. Kind of fun, right? So we're just going to use cosine of theta, which is adjacent over hypotenuse. Well, adjacent on this right triangle, here's the right triangle I made. Adjacent is L minus h, right? See how it's L minus h? Okay, make sure that makes sense. And then hypotenuse is just L. So then if I solve for h ends up being L times 1 minus cosine. Obviously skip some algebra steps here. Check it for yourself. Make sure I'm doing it right. I am. I'm so used to this because I've done a lot of pendulum problems, okay? But make sure you can do it, okay? Now, energy conservation, E1 equals E2. Plug in, right? So E1 is entirely gravitational potential since it's not in motion yet. And then at point 2, we've used up all our gravitational potential and the energy is entirely kinematic, okay? Cool. All right, or kinetic, I should say. Said the wrong word, kinetic, the other K word. All right, then we're just going to substitute in h for L times 1 minus cosine theta. All right, solve for v, okay, multiply both sides by 2. The mass cancels, so the velocity is independent of the mass. And then we find out, once we plug in our numbers, that the pendulum is moving at 3.16 meters per second. Okay, at least the mass at the end of the pendulum is. okay, which is effectively the pendulum because the string is assumed to be massless. All right, cool, right? Okay, something we couldn't have done before. All right, let's do another problem that we couldn't have done with Newton's laws, right? Well, why is this one's not a curved path, right? It's actually a nice ramp that looks like something we would have seen in our force chapter, and then we got level ground. But look at this, we've got a spring. Now we saw the potential energy form of springs, right? Potential energy of springs, or elastic potential energy, has the form of 1/2 kx squared. Okay, now here's the thing. That force came from Hooke's law in a sense, right? When it showed the derivation, it's outside the scope of the class, requires calculus. But what is interesting is that Hooke's law is a force that's non-constant, right? The force was kx. Non-constant force means what? It means non-constant acceleration, all right? And that means that this isn't simple to find. It's non-constant acceleration. In fact, the form of the non-constant acceleration is rather complicated. In fact, it ends up being the mathematical form of the non-constant acceleration of an oscillating spring is identical to a swinging pendulum as long as the angle of the pendulum is small. Okay, pretty amazing stuff. You wouldn't think the two are the same, but they are. Okay, you can actually make an argument, like a visual argument, for why they need to be the same. But and we will discuss that in a later chapter. But don't let me get ahead of myself. Okay, so example 5. All right, so a block with a mass of 10 kilograms is released from a frictionless ramp with a 30-degree slope. All right, travels 1 meter down the slope and then 1 meter along the surface. Okay, no friction anywhere. All right. And then if the spring has a spring constant of 800 newtons per meter, right? Remember, that's how spring constants are expressed: force per meter, force per distance. How far will the spring compress? All right. So here's our points 1 and 2. All right. We're going to acknowledge that H is going to be found through a right triangle. Okay. All right. Notice that at point 1, the block isn't in motion yet because it's just started. And at point 2, when the spring is fully compressed, there's also no motion. So that means that E1 equals to E2 is just going to become, well, look, because the velocity 1 is 0, velocity 2 is 0. It's just going to become potential equals potential, right? So it's just gravitational potential getting converted completely to elastic potential. Now, that's not to say the block wasn't in motion, right? If we were asking for the velocity right here, we could find it, right? We could, find some middle point, point 1, point 2, or 1.5, right? But we weren't asked for that, so we can just relate potential to potential. All right, then we just solve for x. All right, the compression of the block. There we go, plug in our numbers. And there it is, 35 centimeters. All right, pretty far it's a big spring, right? So the spring compresses 35 centimeters by just using conservation of energy, right? And acknowledging that the kinetic energy canceled. Okay. Now, what about this 1 meter? Didn't come up at all, because if there's no friction, this flat ground doesn't matter. The energy doesn't change when it's moving across the flat ground. It had a certain amount of kinetic at the bottom once the gravitational potential energy was converted to kinetic energy, and that kinetic energy would remain unchanged until the spring started to convert that kinetic energy into elastic potential energy. Okay? All right, concept question. 2 children are shown sliding down water slides of the exact same length. Okay? One has a concave curvature in the middle, and the other has a convex curvature in the middle. All right? So, then you can see which kid responds to which, or corresponds to which type of slide. Assume the slides are frictionless. All right? What does conservation of energy tell us about the final speed of each child? Tells us the same. All right? The 2 children have the same final velocity because they have the same height. Right? So the gravitational potential energy without friction must convert to the same kinetics. So they must both have a final velocity of root 2 gh. Right? Absolutely. That can't vary because there's no friction. Okay, if there's friction, it could change. Okay, all right. But here, no friction. They must have the same final velocity. Okay. Well, what does conservation of energy tell us about the time it takes each child to get to the bottom? Nothing. Okay. Energy tells us nothing about time or acceleration. That's one of the big limitations. It's incredibly useful and a simple way of solving certain problems, but you have to be aware of what types of problems it's well suited for. Okay. All right. Finally, do the 2 children get to the bottom at the same time? Well, okay, they arrive at the same speed. It means they get there at the same time, right? Wrong. Okay. Karine would have a greater average velocity, so she would make it to the bottom first. I mean, think about it, right? Paul is hardly moving at first, right? He's really gradually picking up speed. By the time he finally starts to pick up speed, maybe, right here, Karine is already, almost all the way down, right? And so sure, he starts to speed up a lot all of a sudden, but she's already at the bottom. right? I mean, what if his slide was even more gradual, went way out here and then suddenly dropped off, right? Definitely curving to be at the bottom first, right? So, you can have the same final velocity, but not get there in the same amount of time, all right? Because your average velocities are different. Just because you have the same initial velocity and the same final velocity does not mean your average is the same. Why? Because the change in velocity for Paul and Karine were not linear, okay? Because their accelerations were not constant. Why were their accelerations not constant? Because the slides are curved. These aren't ramps. These aren't like constant slope ramps, all right? So I know, right? We're talking about different stuff because we're very careful to keep all our ramps constant and not talk about curved surfaces before, okay? Because we couldn't really do much with it, right? Not with our, our force diagrams and our components and all that. But energy is in some cases a kind of broader useful tool. All right, so let's do a couple more. All right, first one more concept question. Okay, so a heavy object is released from rest at point 1 above a spring. The object falls and contacts the spring at position 2. The spring achieves maximum compression at position 3. Fill in the table below to indicate whether each of the quantities are positive, negative, or 0 during the intervals 1 to 2, 2 to 3, and 1 to 3. All right, so let's consider the first interval, the 1 to 2 interval. What happens to the kinetic energy? It increases. What happens to the gravitational potential energy? It decreases because it's gone down. Right? Gravity is in positive work, which means gravitational potential energy must decrease. What's happened to the elastic potential energy between points 1 and 2? Nothing, because it hasn't contacted the spring. No spring, no elastic energy. Okay? Well, point 2 to 3, okay, now we're actually into the spring. All right, so what happens to the kinetic energy? It decreases because the spring is going to start converting some of that kinetic energy into elastic potential energy. What happens to the gravitational potential energy between 2 and 3? Well, it actually also decreases, right? Because it's still going down. It's still losing gravitational potential energy. So not only is the spring converting kinetic energy into elastic potential energy, it's also converting gravitational potential energy into elastic potential energy. And, it's definitely going up. It's storing energy. The spring is storing energy. There's a positive increase in the elastic potential energy. All right, but what if we skip point 2 and go straight from 1 to 3? Because that's the thing about the idea of energy and comparing between points. You don't have to go from 1 to 2 and then from 2 to 3. You can always skip, okay? All right, well, if we go from 1 to 3, our change in kinetic energy is 0. Why is that? Because it started at rest and it finishes at rest once the spring is maximally compressed. All right, what happens to gravity? It decreases, okay? Because it decreased both from 1 to 2 and from 2 to 3. And what happened to elastic? Well, it went up because there's no change from 1 to 2, and from 2 to 3, it started storing energy. All right, cool. All right, now let's actually kind of do this problem, right, of a block falling on a spring, but do it with numbers, right, not just a concept. Okay, here's the picture, all right. But instead of falling, I'm going to have it start compressed. So it's like we're starting at point 3, and we're looking at it bouncing back up, because of course that would happen, right? It would kind of bounce back and up forever if there was no friction or air resistance. All right, so a vertical spring is compressed with a mass of 731 grams on it, okay? So here it is compressed. All right, the spring constant is 443 newtons per meter. All right, it's compressed a distance of 4.92 centimeters. If the spring is then released from rest, what will be the velocity of the mass when it first leaves contact with the spring? What maximum height will the mass reach? And how much time does the mass spend in the air, okay? All right, and part C, we're obviously not going to be able to use energy for. All right, E1 to E2. Okay, that's going to be useful for part A. All right, we're going to want to relate the gravitational potential energy at 1, the elastic potential energy at 1, and the kinetic energy at 1. Then we want to relate the gravitational potential energy at point 2 and the kinetic energy at point 2. All right. Now notice I left off elastic potential energy at point 2 because at point 2 that's once the mass is leaving the spring. So we know we can't have any elastic potential energy at point 2. I could have wrote it in, but then I feel like I would just immediately cross it out, and so I didn't. But there actually is some other things I'm going to immediately cross out, namely the gravitational potential energy, because I'm defining y naught as 0. Okay, that's my coordinate system. Likewise, since it started at maximally compressed, it doesn't start with any kinetic energy. Okay, all right. So then once we cancel out those two terms and solve for v2, the final velocity when the mass leaves the spring and the spring becomes back to its rest length. All right, then the expression is going to look like this. We just plug in our numbers and solve for our velocity, about 70.9 centimeters per second. Okay, now on to point B. Point B, we want to find the maximum height. All right, I think it's going to be easier to relate E2 and E3 because we already have V2. Right, so we might as well just carry on that number right? No intermediate rounding though. Make sure to save this in your calculator. All right, so my final energy at 3 is just all gravitational potential energy. I'm not bothering to show other ones and canceling them out because I want us to kind of get used to expecting that they're all going to be 0. So it's just be all gravity up here at y max, gravitational potential energy, that is. All right, and then at point 3, all right, it's actually this is 3 and this is 2. I switched the order. Excuse me on that. All right, so really this should say 3 and that should say 2 based on the way I wrote it there. Right, I just swapped the sides, but wouldn't have any effect on the sides or anything. Okay, so then I'm just going to solve for y max, and it's just v2 squared over 2g based on my energy conservation, and plug in our numbers, and there we go. We get a maximum height of 2.56 centimeters, right? So less than the compression, okay? Which makes sense, right? Because the compression had to actually work against gravity, and it depends on the spring constant. If the spring constant is really big, then we could actually get a value here that's bigger than the compression distance. Okay, and then for part C, how much time does it spend in the air? For that one, I'm just going to use kinematics, specifically this equation. All right, V final equals V initial minus GT, minus GT because G is in the opposite direction of positive Y change. All right, because basically my coordinate system is that positive Y is up and gravity points down, hence the negative. Furthermore, V final is going to be defined as negative V2 because that's once it returns to contact with the spring, because that's going to be the total time in the air. This isn't the time to maximum height, it's the total time in the air. And V1 is V2. Because the idea, right, is that it's going to start here, right, in motion, go up to the peak, and then come back down, and when it returns, it's going to have the same magnitude and velocity, but in the opposite direction. Hence, negative V2 for V final, and positive V2 for V initial. Okay, and the V2 is none other than this value right here. All right, so plug in my numbers, negatives cancel out, and then my time in the air is just 2V2 over G. All right, this is actually an expression we've seen before, but it would be 2V naught over G, right? That's like for free fall problems, right? Throwing something straight up in the air. Plug in my numbers, and it's in the air for 0.145 seconds, all right? So about 15% of a second, right? 15/100ths of a second. Okay, cool. Hopefully that looks good. All right, let's see, I think we have, last one. Okay, example 7. All right, this one's complicated just because it's got an angle to it. Okay, and it's the whole idea that when the spring compresses, two things are happening, right? It's going to be still losing gravitational potential energy, but also gaining elastic potential energy, but at this time at an angle. All right, so what does that look like? Well, on the one hand, it's a simple problem because there's just points 1 and point 2. Okay, and there's a right triangle we have to care about here. All right, the right triangle is going to be formed by H as one leg and a hypotenuse that is equal to D plus X. I guess I kind of drew H kind of off to the side, almost like there's an extra distance here. But that was just kind of for convenience. This is supposed to be a straight line. That's sort of like it's supposed to match up with D. Okay, but the point is that the hypotenuse is D plus X, and one leg of the triangle is H. Okay, all right. So look, every problem starts the same. E1 equals E2. All right. So initially there's just gravitational potential energy, and at that point 1, and at point 2 there's just elastic potential energy. So there's no kinetic on either end. Started at rest. Finished at rest. Okay, that's good. All right. Okay, that keeps things simple, right? Well, this next part isn't terribly simple because you got to think what H is. Well, H is d sine theta plus x sine theta. Okay, it's also just d plus x times sine theta if you think of it, right? Because it's just this component of the right triangle. All right, confirm that for yourself, but right, that is in fact the value of H. So then we're going to substitute that in. Okay. All right, and now we just have to solve for x because x is our single unknown. When we look at this expression, it's an expression where we got to use the quadratic formula to solve for x, because we have an x squared and an x. So I go ahead and do that. My b term is mg sine theta, so my negative b is right there. Then plus or minus b squared, all right, and then minus 4ac. So a is just 1/2 k, and then c is mgd sine theta. So when I minus 4ac, it just becomes this. All right, because the 4 times the 1/2 becomes a 2. The negative times the negative becomes a positive. All right, and then my 2a in the denominator is this 2 times negative 1/2 k. All right, which just becomes negative k, which means the leading negative in the denominator cancels the leading negative in the numerator. Okay, and now let's plug in our values. Oh, and by the way, only the positive solution, so the plus here, only the plus, I should say, gives us a positive solution. So we can reject the negative. All right, so then just with the positive left, plug in all our numbers. All right, let's plug in the spring constant where necessary, the mass, the mass where it comes up, right? And so on, okay? All right, see, did I, oh, maybe I did leave out a 5.6 there. I gotta check. I think I might have, because I have M, I got a K. It looks like I left off 5.6. I was moving fast. Because I have my G and I got my D. Yep, I left off. I'll add that to the notes and re-upload them. Because right here, there should be a 5.6 kilograms. But I missed that when I was writing it. Okay, or 56, excuse me. 56 is here, but it should also be there. Okay, and if everywhere else I did remember the 56, but I dropped it right there. And that will make a difference. All right, so it'll make my X a little bit bigger. All right, here's the X I got, so 0.158 centimeters, but it will in fact be larger because I have it, there's another term in there, okay? All right, but the idea holds the same. Here, symbolically, it is correct, but when I plugged in the numbers, I made a little mistake. Okay, all right, so we saw some conservation energy problems where there's just mechanical energy. In the next lecture, you're gonna see all the same type of problems, but with friction. Just one extra level of complexity. We're ready for that, right? All right. Well, thank you so much for watching this lecture. I hope it was interesting, and I'll talk to you all soon.